Hi everyone, and welcome back to the channel. If you're new here, I'm Ryan, a Cambridge mathematician and ex-step marker. Today, we're diving into some graph sketching questions. Now, if you haven't seen my last video, go and give it a watch because I dived into a really good method for attempting graph sketching questions, and we'll be using some of those techniques today. Graph sketching is one of those fundamental skills that helps build up your intuition for mathematics. Whether it's finding the asymptotes, identifying key features, or just understanding how functions behave, these methods can help you across all areas of mathematics. Okay, so let's get straight into it with the first question. Now this one is a step 2 question from 2011 that really relies on curve sketching, both in part I and part II. I'll give you a few seconds to pause the video and take a screenshot, and if you want, have an attempt of the question. Okay, so for part I, they want us to sketch this curve. The curve of y equals the square root of 1 minus x plus the square root of 3 plus x. So I'll write that down now. So we want to sketch y equals the square root of 1 minus x plus the square root of 3 plus x. Okay, so that's our function. So first we want to go through the steps. We want to know what type of function it is. So is it a one-to-one, many-to-one, one-to-many, or many-to-many? Well, from this one, we don't know whether it's a one-to-one or many-to-one, but we do know it's definitely not one-to-many because we're only getting one y value out of this. So type of function is either a one-to-one or many-to-one. Okay, so then next we want to work out what our domain is. Well, it's actually not too bad to work out our domain. I can tell here I'm not going to get any infinities anywhere because I'm not dividing by an x, but I noticed that I cannot go past x equals 1 because this first function, the 1 minus x, has to be positive or else the square root would be imaginary, which I can't have. So the domain, so for square root of 1 minus x, I need x less than or equal to 1. And then for the square root of 3 plus x, I need x greater than or equal to minus 3. So overall, I need minus 3 less than or equal to x less than or equal to 1. So that's my domain. So next we want to think about any symmetries we get. So symmetries. Well, we only really need to do the obvious ones for this. So we want to think about what does y of minus x look like. Well, that looks like square root of 1 plus x plus the square root of 3 minus x, which isn't the same as y of x and it definitely isn't the same as minus y of x. So we have no symmetries. No obvious symmetries anyway. However, don't need to do this for this question, but you can actually see a symmetry elsewhere. If I instead look at y of minus 2 minus x, that's equal to the square root of 1 minus 2 minus x plus the square root of 3 plus minus 2 minus x, which after changing looks like 3 plus x plus the square root of 1 minus x. Okay, so what does that mean? Well, it means that if I shift my graph 2 to the right, then I have a symmetry because this is equal to y of x. So that essentially means I have a symmetry about x equals minus 1. Which kind of makes sense because of where we are. We're going between minus 3 and 1, so the middle of those two would be at minus 1. Okay, so for the next step, crossing points. So where does it cross the axes? Okay, so let's do the easy one. When x equals 0, we have y of 0 equals the square root of 1 plus the square root of 3. So that's a y-intercept of 0, square root of 1 plus square root of 3, which is just 1 plus square root of 3. 0, 1 plus square root of 3. Okay, easy. So next is when y equals 0. Well, what do I have when y equals 0? I have that the square root of 1 minus x plus the square root of 3 plus x is all equal to 0, so therefore the square root of 1 minus x equals minus the square root of 3 plus x. Okay, so this is where it goes a bit wrong. If you look at the left-hand side, I have a positive, as long as it's not 0, and if on the right, I have a negative. So the only way these two equations can match is if they're both 0. But I can't have these both equal 0. For the left-hand side, I would need x equals 1. For the right-hand side, I would need x equals -3. So there is no x-intercept. Okay, we've done the crossing points. So next is on to any vertical asymptotes. And from earlier, it's quite easy to see that there is no vertical asymptotes. I'm not dividing by an x anywhere. I'm not going to get an infinity. And then horizontal/oblique asymptotes. Well, don't even need to consider them. There might be one. I mean, there isn't actually going to be one for this equation, but I don't need to consider them because I'm only considering between -3 and 1. So there is no horizontal asymptotes, so I can again write none. Okay, so next, turning points. Well, to have a turning point, I need to do the gradient. So if I have dy by dx is equal to, so you'll have to use the chain rule here, I get -1/2, 1 minus x to the power of -1/2, plus another half, 3 plus x to the -1/2, and I then want to set that equal to 0 to find the turning points. Okay, so again, I can just rearrange. So I've got 1/2, 1 minus x to the -1/2 equals 1/2, 3 plus x to the -1/2. Can cancel out the halves. Can take 3 plus x to the other side and 1 minus x to the other side to get 3 plus x to the half equals 1 minus x to the half. Okay, so knowing these be equal, I'm going to square both sides to get 3 plus x equals 1 minus x. And then I will have 2x equals -2, x equals -1. And then to find the y value, we plug it back in and we end up with y equals the, what will we have? We'll have square root of 2 plus the square root of 2 equals 2 root 2. So our turning point is at -1, 2 root 2. Okay, so we've done turning points. So all that's left is that last point, which you often don't have to do, but for here we kind of do because we want to know what's happening at the two endpoints. So the last part is plot some points. So here, the only ones I'm interested in are at the key points, which are at -3 and 1. But this should be pretty simple to work out. X equals -3, I get y of -3 equals square root of 4 plus 0 equals 2. And then at x equals 1, I get y of 1 equals 0 plus the square root of 4 equals 2. Again, hinting at that symmetry. So what do I need to do next? Well, I need to actually draw this. So let's have a quick sketch of it. Draw it nice and big. Just looking at my values, they've all been positive so far, so I don't really need to draw a negative axis. I'll draw a little bit of one. So this is x, and then this is y. So what do I know? I know we have endpoints at y equals -3. So let's say here, let's say this is -3, -2, -1, and then I have 1 and 2. Don't really need to go beyond that because I'm only looking between -3 and 1. So I know that I have a point at -3, 2. So plotting on the points for the y-axis. So I know I have at -3, I have a value of 2. So that looks something about here. Similarly, at 1, I have a point here. Okay, so then only other point I actually have is my turning point, which is at -1, 2 root 2. 2 root 2 is somewhere just beneath 3, so it's going to be somewhere around here. And then that's my only turning point. And it's quite clear from here that that will be a maximum because I've got no other options. I've got to start here and I know I've got to reach that point. There's no discontinuities here, so I've just got to increase up to there and then come back down. Again, you can see that symmetry at -1. Okay, so that's it for the graph. So looking at the next bit, use your sketch to show that there is only one real value of x satisfying square root of 1 minus x plus square root of 3 plus x, essentially our function, equals x plus 1. So essentially what I need to do is draw on the line x plus 1 and look for how many solutions there are. Well, this should be pretty easy because I can already see the line x plus 1 looks something like, it's going to go through -1, it's going to go through there, it's going to go through there. And that's pretty easy. So the only solution is clearly at this point here. So using the graph, our graph, there is only one intersection at x equals 1, y equals 2. So the solution is x equals 1. Okay, so next, part 2, because essentially we need to repeat this, but we've now got 2 sketches rather than just one. It's not as easy to draw the square root of 1 minus x as it was x plus 1. So we'll do the exact same thing, we'll just move through it a bit quicker. Okay, so for the sketch of y equals 3 plus x plus the square root of 3 minus x, starting off with the function, again, many to one. The domain, similar to last time, we want it to be between -3 and 3. Okay, and then any symmetry. Well, now we have a bit of an obvious symmetry in that y of minus x equals the square root of 3 minus x plus the square root of 3 plus x. Now that's equal to y of x. So it's an even function. Okay, so then we move on to the intercepts. So when x equals 0, we get y equals 2 root 3. And when y equals 0, I again get the square root of 3 minus x equals the square root of 3 plus x. And there's no x where both sides are 0, so because one's positive and one's negative, we again get no solution. So there's no x intercept. So vertical and horizontal asymptotes. Again, there is none. That's pretty easy. And last but not least, the turning point. I can likely have a guess at where the turning point is going to be because of the symmetry. I assume the turning point is going to be at x equals 0, but we will prove it just to be sure. So dy by dx is equal to -1/2 3 minus x to the -1/2 plus 1/2 3 plus x to the -1/2. Put that all equal to 0, rearrange, you end up with 3 minus x to the -1/2 equals 3 plus x to the -1/2, to the -1/2. Squaring both sides and multiplying, you get 3 minus x equals 3 plus x. Rearranging, you get x equals 0. And at that point, we have y equals 2 root 3. Okay, and looking at plotting some points, namely the end points, we get that y of 3 is equal to square root of 6, and y of -3 is also equal to the square root of 6. So again, plotting our graph pretty big. And leave enough room here because I'm going to have to add another sketch to this. So again, going -1, -2, -3, -1, -2, -3. And then we need to go up to 2 root 3. So that's 1, 2, 3, and 4. Because 2 root 3 is just below 4. Okay, so I know, similar to last time, that at -3 we're at root 6, which is about 2.5-ish. So on my graph, somewhere about here. Same at 3, similar point. And then I know at 0, I'm at 2 root 3, which is about 3.5. So I think I'd look something similar to last time, but more like this. Okay, and that's everything I need to do for the first drawing. And then I need to do the same for the second drawing, which is 2 root 1 minus x. So for y equals 2 root 1 minus x, function, same as before, many to 1. Domain, where it's more open this time, I just need x less than 1, less than or equal to 1. Symmetry, where y of minus x equals 2 root 1 plus x, so no real symmetries there. Crossing points, well, I have x equals 0 gives me y equals square root of 2, and at y equals 0 I have 0 equals 2 root 1 minus x. So here it's easy to see that at x equals 1 I will have a x-intercept. That's useful, the first x-intercept we've had. So that's at 1 comma 0, and that's at 0 comma root 2. So next we need to look at horizontal and vertical asymptotes. Again, pretty obvious from this. Not going to get any horizontal or vertical asymptotes. As x goes to minus infinity, it's just going to go up to minus infinity. We're not going to get it tending towards anything. So then we need to look at turning points. Now I know what this graph is going to somewhat look like. It's going to look similar to the square root of x, and I know the square root of x doesn't have any turning points, but we'll just double check. So we have dy by dx equals, and it will be minus 1 minus x minus a half. That's equal to 0. And then what we have is that essentially 1 over the square root of 1 minus x is equal to 0, and there is no solution to that. I can only get infinity, don't really care about that. So no turning point. And then just plotting points. I just want to look at the endpoints again. Well, I have at the endpoint plugging in x equals 1 gives me y equals 0. So it's again 1 comma 0. Okay, and bringing this all back together, plotting it on the graph, we end up with, we know it crosses through 1, 0. I also know it crosses through 0 root 2, which is somewhere around here. And then I know that because there's no turning points, and to go from here to here it has to go down, and it's got to continue going up here. And now the only thing I need to check is, do they actually intercept here? So there's at most one intersection, but I need to check. The way to check that is just, is this point at minus 3 above or below the end point for the previous graph? So all I need to do is plug in at x equals minus 3, I have y equals 2 times the square root of 4 equals 4, and that is definitely above 2.5, so there is one crossing point. And that's somewhere in the region between minus 1 and minus 3. Okay, so last but not least, I need to actually solve this equation. So to solve the equation, I need to be a bit careful because there's going to be a lot of modulus signs that are lost in this, especially when we're squaring. We're going to add additional solutions to it. So I just need to be careful. I know where my answer should lie, so I need to be double checking that at the end. So I start with 2 root 1 minus x equals the square root of 3 plus x plus the square root of 3 minus x. So first off, I'm just going to square both sides, see what happens. So get 4 times 1 minus x equals 3 plus x plus, this becomes 3 minus x, and then I've got them multiplying together to give 2 root, 3 plus x times 3 minus x is pretty simple because that's 9 minus x squared. Okay, so then rearranging, 4 minus 4x, bring all these to the other side, minus, they cancel out, just notice that, minus 6 equals 2 root 9 minus x squared. So that gives me, divided by 2, I'm going to get minus 1 minus 2x equals square root 9 minus x squared. Okay. So, oh yeah, so the left-hand side can be positive as long as x is greater than less than minus a half, which the region where my solution is, that's true, that's good. Okay, so next I'm just going to again square both sides. I should get rid of all my square roots. So minus 1 minus 2x all squared equals 9 minus x squared. Expanding, I get 1 plus 4x squared equals 9 minus x squared. So overall 5x squared plus 4x minus 8. So then trying to solve this, I end up with x equals minus 4 plus or minus the square root of b squared is 16 minus 4 times 5 times minus 8 all over 2 times 5. And then just because I see a lot of 4s and 16s about, I'm going to cancel out some of the bits. So I end up with minus 2 plus or minus the square root of 4. The two negatives cancel and divide by 4 gives me plus 5 times 8 all over 5. That's then equal to minus 2 plus or minus the square root of 44 all over 5, which is, I can take a 4 out, so it's minus 2 plus or minus 2 root 11 all over 5. Okay, so I've got two solutions. I know there's only actually one solution, but one of these is going to be positive, the other one's going to be negative. From my graph, I only want to take the negative solution. So my final solution is x equals minus 2 root 11 all over 5. Okay, so that's the first question done. Pretty much all relied on just being able to sketch a couple of graphs well, and then just using a bit of logic to see what analysis you can take from that. Now, if you found the video helpful so far, please consider subscribing. It really helps out the channel. So let's get on with the next question. So this is question 2. It's a step question from 1999, so it's quite an old one, but it's still pretty useful. So I'll give you a few seconds to pause the video, screenshot it, have a go at it. So let's get straight into it. We've got the equation y equals x over the square root of x squared minus 2x plus a. They've asked us to take the square root being positive, so we just need to be careful when we take square roots that we need to take the modulus of whatever we get out. Okay, so they asked me to show that if a is greater than 1, then c has exactly one stationary point. Okay, so first off, we just need to find the stationary point. So we need to do dy by dx. And to do that, I'm going to use the product rule by rewriting the equation as x times by x squared minus 2x plus a all to the power of minus a half. And then doing the product rule, you have x squared minus 2x plus a all to the power of minus a half plus x. And then I'm going to need to use the chain rule for this bit because I'm going to get out 2x minus 2 from the inside. And then a power comes down to get minus a half, and then x squared minus 2x plus a all to the power of minus 3 over 2. Okay, so then just to make it a bit more simple for myself, I'm going to take out this final factor as a common factor. So I'm going to have x squared minus 2x plus a all to the power minus 3 over 2 multiplied by, and then I'm going to have an x squared minus 2x plus a from the first term. And then I'm going to have minus a half times by x 2x minus 2. Okay, so then that means that after slightly neatening it up, I have x squared minus 2x plus a, and then it'll be minus x squared plus x equals x squared minus 2x plus a minus 3 over 2, and then that cancels with that, and I'm left with a minus x. So writing it a little bit more neatly, a minus x all over x squared minus 2x plus a to the 3 over 2. Okay, so if I'm looking for a stationary point, I want this to be equal to 0. But I need to be slightly careful here. If the denominator was 0 at the same time as the numerator was 0, I might not get a stationary point. But they've told me an interesting fact. A must be greater than 1 here. So this value on the bottom, x squared minus 2x plus a, can only be 0 if the discriminant is greater than 1. But the discriminant here is b squared, which is 4 minus 4 times by 1 times by a, equals 4 minus 4a, which is equal to 4, 1 minus a. And since a is greater than 1, this is less than 0. So the denominator can never be equal to 0. So therefore I only have one solution when x equals a. And that's all I need to do for the first part. So now for the second part, I'm going to have to use some of this, but I now want to sketch C when we have a equals 2. So when a equals 2, I have the equation y equals x over square root of x squared minus 2x plus 2. Bottom doesn't neaten up too much, there's not much I can do there, but we just need to go through the same steps as we've done before, where we write our function type is a many to one. Our domain, well, they've specified nothing in the question, and I know from previous analysis that the bottom can never be equal to 0, so I'm not going to get any singularities. The domain is all of x. Okay, so then symmetry. Well, y of minus x equals minus x all over the square root of x squared plus 2x plus 2, so no symmetry. So then crossing points. When x equals 0, we have y equals 0, so that's our y-intercept, and then when y equals 0, we have x over the square root of x squared plus 2x plus 2. Well, the bottom's never equal to 0, so the top's only equal to 0 when x equals 0. So we only have one crossing point at 0, 0. Okay, so then we need to look at vertical asymptotes. Well, we know the bottom's never equal to 0, so we have none. Horizontal asymptotes. This is where it gets a bit more tricky, and we need to be careful with that square root. So, what happens as x goes to plus or minus infinity? As x goes to plus or minus infinity, well then y tends to, the highest order on the top is x, so that's easy, x, and then we have on the bottom the square root of x squared. So what people normally do is just cancel them out and go x over x. It's not that simple, because we've said we're taking the positive. So what this actually is equal to is x over the modulus of x. So then as x goes to positive infinity, y tends to infinity over infinity, which is 1, it's easy. But then as x tends to minus infinity, we get y tending to minus 1, because it's minus infinity over the modulus of minus infinity becomes positive infinity. So we have two different horizontal asymptotes when it's plus infinity or minus infinity. So we need to be a little bit careful there. Okay, so next is turning points. And this is quite easy because I've actually already found it. Because I now know I have a equals 2, which is bigger than 1, as we specified earlier, then I have a turning point at x equals a, which is equal to 2. And then I can plug in to find y. So y equals, and then I have 2 over the square root of 2 squared minus 2 times 2 plus 2, which is equal to 2 over root 2, which is equal to root 2. So I have a turning point at 2, comma root 2. Okay, so that's all the analysis I need to do, and I just need to bring it all together and actually draw the function. So let's draw it out. So x and y, 1, 2, and 3, and then minus 1, minus 2, minus 3, and 1 and 2, minus 1, minus 2. So drawing on the facts that I know, well, the first one is that I have a crossing point at 0, 0. Next one is that as we go to positive infinity, I have a horizontal asymptote at 1. And as I go to minus infinity, I have a horizontal asymptote at -1. And then lastly, I know that I have a turning point at 2, root 2. Root 2 is just a bit bigger than 1, so we'll just put it somewhere up here. Doesn't matter too much where it actually is. Okay, so let's first look in the positive domain. So we know we have to start at 0, 0. So if I start at 0, 0, I know I need to get up to the point at 2, root 2. So I've got to increase, and then I've got to hit this maximum. And we now know it's maximum because it can't be a minimum. And I know I've got to, as I get to infinity, come back down. And I know I don't go beneath 1, because if I did, I'd have to come back up, and that would mean I need a minimum. But I know I only have 1. Okay, it's pretty simple on that side. But as I go to minus infinity, it's even simpler. I don't have a turning point, and I need to go to -1. So it just means that I slowly go to -1 as I go to minus infinity. And that's the whole graph drawn. Pretty simple. Now let me just label on some of my points. So that should be 2, root 2. I've labelled on 1, I've labelled on -1, and the origin's pretty obvious. Okay, so let's move on to part 2. So part 2 is when a equals 1. Now this is a bit different from what I did before because I specified a must be bigger than 1. But let's go with that. So the graph is equal to x over the square root of x squared minus 2x plus 1. Ooh, noticing that that is just x over the square root of x minus 1 all squared. And then this is where you need to be a bit more careful. You can't just cancel them out. You can't just say that that's x minus 1 because it's not always positive. So what we need to do is put a modulus over that. And then I can continue on, doing the same as what I did before. Function type. Many to 1. Domain. Need to be a bit more careful here. Still nothing in the question stopping me from doing all of x. However, x equals 1 is going to give me an infinity. So domain is just everything other than x equal to 1. Okay, symmetry. F of minus x equals minus x over modulus of minus x minus 1. That's just minus x over x plus 1. It isn't symmetric, no symmetry. Okay, now for crossing points. So it's going to be the same as before. When x equals 0, I get y equals 0, and then when y equals 0, I get x must be 0. So therefore, my only crossing point is again at 0, 0. Okay, vertical asymptotes. Okay, I've already kind of identified it, but I'll just double check it is actually a asymptote. So at x equals 1, I get y equals 1 over infinity. So yes, so it is a vertical asymptote. Okay, pretty easy. Horizontal asymptotes. This again, exact same as before. As x tends to plus or minus infinity, y tends to x over the modulus of x. So we have that as x tends to infinity, y tends to 1, as x tends to minus infinity, y tends to minus 1. Okay, pretty simple. Turning points. Okay, so a little bit more tricky, can't use the analysis I did before. However, I only required a to be greater than 1 partway through. I can still use the fact that dy by dx is equal to a minus x over x squared minus 2x plus a all to the 3 over 2. And then I can just plug in what a is. So it's 1 minus x all over x squared minus 2x plus 1 to the 3 over 2, which, as I did before, is 1 minus x all over x minus 1 all squared to the power 3 over 2. And there's a bit of a cheeky analysis you can do, which is 1 minus x all over, and it'll be x minus 1 all squared multiplied by x minus 1 to squared to the power a half. Okay, and then we can do a bit of cancellation. We can cancel the top with one of the bottom. So this with this, we're left with minus 1. So we've got minus 1 all over x minus 1. And then this is the same as before, it's modulus of x minus 1. Okay, so again, we're looking for a turning point, so we want this equal to 0. Well, this is never equal to 0. When x equals 1, we're getting infinities, and there's no way the numerator can be 0. So no turning points. Okay, so we've done all the analysis we need to. We now just need to sketch it. So we just need to do the same as before. 1, 2, 3, minus 1, minus 2, minus 3, and 1, 2. Bring it down just for a bit more space. Can't draw your graphs too big. X, y, y, minus 1, minus 2. Okay, so let's draw on what I know. First off, I have that crossing point at 0, 0 again. I also have that I have a vertical asymptote at x equals 1. For horizontal asymptote at y equals 1. And at minus 1. Lastly, I don't have any turning points. So this is all I know about the graph. Okay, so what can I say? Well, again, it's always good when you've got an asymptote, consider each region separately. So let's consider x greater than 1. So the right-hand side of this graph. Okay, so what's going to happen in that region? Well, because it's an asymptote, I either come from positive infinity or minus infinity. If I come from minus infinity, I need to come from the bottom, and I know I need to hit 1 as I go to infinity. That means at some point I have to cross the axis. But I know in this region I do not cross the axis because I found all my crossing points, so that can't be possible. Instead, I must come down from positive infinity and just go towards 1. I can't go beneath it because that would mean I have a turning point, which I know I don't have. So that's it for that side. For the left-hand side of this, I can again either start at positive infinity or minus infinity. If I start from minus infinity, I come up. I have to go through this crossing point, but then I need to get back down to minus 1. So I have to cross the axis again. But I know I don't do that because I've found all my crossing points. The other option is I could have a turning point on 0, 0. But I also know that that's not true because I found all my turning points as well. So this cannot work. The other option is I come from positive infinity and I come down and I go through that crossing point and I slowly head to minus 1, which is in fact what does happen. So this is your final graph, and this is the full question complete. And that's it for today's video. How did you find these graph sketching questions? Did you find any interesting features or any interesting methods that I didn't see? I'd love to hear your thoughts. If you enjoy working through these problems with me, please hit that like button, and if you're new here, please consider subscribing. It really does help the channel. Also, be sure to share this with any friends that might be a tempting step, as it could really help them out. Until next time, keep practicing those sketches, and I'll see you in the next one.